Okay, we can go ahead and start our webinar. Well, good afternoon, everyone, and thank you all for joining our June TRANS-IPIC webinar. For those who are joining us for the first time and don't know me, I'm Bassem Andrawes. I'm a professor in the Department of Civil and Environmental Engineering at the University of Illinois. I also have the pleasure of serving as the director of TRANS-IPIC UTC, which is hosting and organizing this webinar. Today, we're going to have two of our projects highlighted by the researchers conducting the work. The first is by Professor Pinar Okumus, who is also an associate director of TRANS-IPIC at the University of Buffalo. And the second is, of course, project that I am serving as the PI, and I am joined today with my student, Alexander Chen, who will be also giving the talk today. So before we go ahead and start, I just want to make very few remarks and notes. As you know, we try to hold our webinar every month. So this is the June webinar. However, we starting this year to have quarterly faculty meetings. So next month, there will be no webinar because we will have our quarterly faculty meeting. And we're still, collecting the availability of everybody for that meeting, but it's going to be between July 17 and July 24th. So if you haven't responded to Chris's email, please do so and indicate your preference between these two dates. And I'm expecting that in that coming meeting, we will be discussing our next round of proposals. We just came back from UTC directors meeting, and I have some information I want to share with the faculty and, about the funding for year 4 and for the upcoming call for proposals. Also, you should have received an email from Chris about TIP 2027, our annual workshop where we really get together in person and discuss our research. So that date has been set on April 16 of next year. Same Big Ten Office and Conference Center, which many of you are very familiar with by now. So please mark your calendars and save that date. Without any further ado, I would like to start with our first speaker for this webinar, Professor Okumus. And let me just say a few words about her. She's, of course, known in the community, and Professor Okumus is an associate professor at the University of Buffalo. Her research advances infrastructure resiliency and longevity. She focuses on structures that can be rapidly built, repaired, replaced, and reoccupied when deteriorated due to extreme loading or environmental exposure. The project that Professor Okumus is going to be talking about today is one of the very exciting projects we have in our center, and basically it's focusing on utilizing machine learning essentially to assess very tricky cracks in bridges, especially shear cracks, as you probably will see today. So I'm looking forward to her presentation. Pinar, please, if you go ahead.
All right, thank you for the introduction. I will be talking about shear cracks indeed in pre-stressed concrete beams. And before I start, just acknowledging Mohammed, Hassan, Lasheen's work. He's the PhD student on this, and he's done all the work. And of course, my collaborator, Dr. Ahami Khorsani. So the motivation of our project is that, like Dr. Andrawes said, there are shear cracks that we observe in pre-stressed concrete beams sometimes during inspection. And then bridge engineers, owners need to know what to do with these cracks. Should they be load posting the bridge? Should they be closing it? Or maybe, the bridge is completely safe. So our proposed solution to this was to interpret these crack widths by relating it to applied shear and stiffness. And what I mean by applied shear and stiffness, and throughout the presentation, will be that this is the shear that caused that crack, and this is that stiffness that's corresponding to that crack width. So we're trying to relate all those to crack widths, in addition to bridge or the beam properties, design details, reinforcing details. And we did that, find the correlation between crack width and applied shear and stiffness through developing machine learning algorithms. So we did develop 3 algorithms for predicting strength, applied shear, and stiffness. And if you've seen me given one of these TRANS-IPIC webinars in the past, you've heard me talk about these 3. So these machine learning algorithms we developed in detail in previous webinars, how we pick the algorithms, how well they do. So actually, I will do a refresher on these 3 quickly, but the main focus of this presentation is a recent test we conducted on a beam to understand how cracked beams respond to loading. Okay, so here's the quick refresher. Like I said, we have 3 algorithms. The first one is predicting shear strength. Because machine learning is data-driven, we collected all the data from the literature, people who tested beams under shear, and there's 804 beams on this. So we will be predicting this point, and of course, this point has nothing to do with crack width. At that point, your cracks are already very large. We're not worried about cracking. But you'll see that we use this prediction to benchmark our applied shear predictions and the total response. The second algorithm we developed is for applied shear. Like I said, applied shear is all these points that correspond to measured crack widths. And if you look at the literature, only actually out of the 804, only 79 beams reported crack widths and shear measurements. But luckily for each beam, you have multiple crack points like this. And multiple load measurements. So we have 409 crack width versus shear measurements for applied shear that we can train, and that's the sufficient number actually for the algorithm that we picked. We take this applied shear and normalize it by the shear strength. That's why we need this shear strength parameter, so that it gives you a better idea of the bridge condition, because saying, your bridge was loaded to 100 kips may not be meaningful, but if you say your bridge was loaded to 80% of its capacity when you saw that crack, it is a meaningful information that you could use to say, okay, that bridge is going to be prioritized before another bridge that may have been loaded to 30% of its capacity. And then finally, the last algorithm predicts stiffness. And for stiffness, there's actually even fewer beams, so only 37 beams in the literature, and 254 crack width versus stiffness measurements, because again, for each beam, you have multiple crack measurements. So this 254 is on the lower end of data size for machine learning, but we worked with what we have. And stiffness, similar to applied shear, we normalize it by the initial stiffness, so this portion of that load displacement curve. So I'm going to jump into the results directly for this part. These are our machine learning predictions. We're using something called Gaussian process regression. These plots you'll see a lot in this presentation. Vertical axis is the test results. Horizontal axis is machine learning predictions. And if you see any dots on this red 45-degree line, that means it's a perfect prediction. We're spot on. And as you can see, our machine learning does a pretty good job predicting the strength, and the large coefficient of variation comes from these outliers. The other advantage of this, the method that we picked, is that it can also give you a variance, which is an indicator of how certain the predictions are. If you wanted to compare that to how well design codes predict the capacity, this is one example. So this is AASHTO LRFD. You can see their mean of the ratio test divided by AASHTO is much larger. That doesn't necessarily mean that they're worse. They're trying to be conservative. That's the intent of the design codes. That's why all the dots are on the upper half of the plot. But it is an advantage to not have that conservatism in evaluation, because what's really valuable for the new bridge design may not be needed for evaluation. And that's what our machine learning does. For applied shear, again, same type of plot. So this is that applied shear corresponding to a crack normalized by shear strength. Horizontal axis is machine learning. We have pretty good predictions, really good error, and a really nice coefficient of variation. And then this is the stiffness predictions. You can see, I will say 18% is acceptable, but you see a large scatter, and then the small size of the data is also apparent from this plot. So this is our stiffness divided by initial stiffness predictions. And then finally, from what you've seen before, we know that not all bridge engineers out there are going to want to run algorithms. So we developed this web interface where the bridge engineer or an inspector populates it with the bridge design features and the crack width, and then it tells them or her the percentage of the load that bridge capacity that the bridge experienced, so 67 here, and 51% of the stiffness the bridge experience when there was that crack. And again, the variance is that indication for uncertainty. All right, so the main part of this presentation, main focus, is on the beam test that we recently conducted. And the reason why we wanted to test the beam was that we wanted to really understand crack beam behavior. Because if you look at the literature, I did tell you we have hundreds of tests, but almost all of those tests, actually all of them, are loading the beam monotonically under monotonically increased loading. So our test loaded the beam to cracking, unloaded, and then loaded it again. So we conducted cyclic loading testing. So now we're saying, okay, if an overloaded vehicle passes through the bridge and is cracked, what will happen to that bridge when it's loaded again? We can understand that from our test. And that also gives us an ability to evaluate the capacity predictions of design codes and our algorithms compared to test data. It allows us to assess our applied shear and stiffness predictions, and you'll see that we use some of the new data to enhance some of our predictions. But first, I'll start with just telling you about the test results and how the design codes and machine learning predicted the capacity. So this was our beam specimen. We tested a 30-inch deep Pennsylvania standard section. If you're not familiar with it, that's similar to an AASHTO type I section beam. It's 20 foot long. We have 4 foot overhang on each side because we did not want the transfer length to interfere with our results. And like I said, we're doing cyclic loading. This is our specimen design. So we have one beam, but we're actually collecting 2 beam worth of data out of it. So we have a weak side. So half the beam, the right-hand side, we call it the weak side, is reinforced with number 3 stirrups at 6 inches. We expect the failure to happen here. On the left-hand side of the beam, we have number 4 bars at 6 inches. We call it the strong side. We know we're not going to be able to fail the beam on the strong side, so we won't be able to get the capacity, but that doesn't mean we cannot collect crack width versus applied load data. So that's what we're getting from the other side. If you're wondering how the new data we collect compared to the 804 beams that are out there, so these box plots show that. So most of the available data in the literature will be in these boxes. And these plus signs are the outliers, and the circle and the square are the colored ones are our beams, our beam, with the 2 sides of the beam. So what is apparent here is that our beam is an outlier for the most part, and that's because most tests in the literature are actually pretty small size. So our 30-inch beam is a fairly large size for this data set, and heavier reinforcement as well. So it is a new data compared to what's available. Our loading protocol, like I said, was cyclic. And the other thing I want to make clear here is that, so this is the beam displacement versus time, our loading protocol. So we load, unload, load, unload, load, unload. One very important thing we can get from this type of testing is that we collect data when we load the beam, and that's your transient crack width. We measure the transient crack width when there's a load on the beam, because this is what all the literature is reporting, because they're running monotonically increasing loading tests. So all the cracks data that we have in the literature is really for really transient cracking. But nobody reports residual crack width. So residual is after you remove the load, what's that remaining crack? And it's important because that is what's measured during inspection. And again, there's no data that links the two crack widths together. So we wanted to get a sense of that. Okay, so before we did any testing, we predicted the capacity using various methods. Our machine learning told us that the beam was going to fail at 550 kips, and all the design codes were much, much lower. So you could see ASHTO is actually almost half of it, half of it. We also ran finite element analysis on this one, and that's this result. So finite element analysis was in between the machine learning prediction and the ASHTO prediction. And then we tested. So here's our test load and displacement response. We have the actuator force versus displacement. You can see we loaded the first cycle. At the end of the first cycle, we actually did crack the beam already in flexure and shear. We unload, and every cycle that follows that, you can see that the initial stiffness is smaller. And then we had stirrups yielding, and 450 kips, we take it as our failure load. We start seeing the plateau. We started seeing, hearing and seeing cracks, falling, and we did not want things to get unstable any further, so we stopped the test here. So it may have gone maybe another 20 kips or so higher, but we take this as our failure load for us. So if I plot that measured capacity on my plot, this is how it compares to machine learning, finite element analysis, and the code predictions. So here the finite element analysis is the winner, and the machine learning the runner-up. And again, measured capacity is here, but it could have been a little bit higher. These were the crack widths that we collected. So we did see those shear cracks. These are the residual crack widths. That's why they're small. But we collected that data from the weak side and the strong side. And then you could see the doubling the reinforcement really does help with the crack width. So much smaller cracking on the strong side of the beam. This plot is showing the same thing, so residual and transient crack widths this time, but we're plotting them together. So these hollow markers on the bottom are the residual crack widths from both sides. So it's nice and small. This is what you saw in that picture. And then these are the transient ones that we measured through testing. So one very interesting conclusion we make from here is that transient crack widths actually can be 2 to 5 times as high as residual cracks. And that's important again because thus residual cracks are what we're measuring during inspection. And then once the stirrups yield, the residual crack widths get much larger as well. This is the new data that we added to the database. So you're looking at the applied shear, again, normalized versus transient crack width. This is all the blue dots are what's available in the literature. What we've added is the colored points. So we added many data points to that plot. And then this is for the stiffness plot. So we added, again, many data points to that stiffness plot. You don't see as many here because a lot of the dots are on top of each other because they have the same stiffness for varying crack widths. Okay, so that's what we learned from the crack beam test. I think the most important thing we learned was that even though your beam is cracked, you may see cracks in the field, but your capacity will still be many times above the, couple of times above the design code predictions. So the second thing we did with our test data is that we tested our machine learning predictions for the applied shear and stiffness. And then we also used some of the new data to see if we could enhance our predictions. So as you remember, we had data from both sides of the beam, so 2 sides, and we used them actually for 2 different purposes. The strong side data, we use it to update our machine learning algorithms. So any data we collect from there is going to be added to the database. And the data we get from the weak side, we never show that to the algorithm. So that's always unseen by the algorithm because we're using it to test the machine learning algorithms to assess the accuracy. So the two sides are similar, as I said, similar dimensions, but very different reinforcing ratios. One issue we have with this is that the shear strength, we didn't test this, the strong side, so we don't know the shear strength of the strong side. So we complemented the test data with data we get from finite element analysis. We calibrated that finite element analysis first using the weak side data, and then predicted the strong side, added it to our database. This slide is showing that calibration. The green line is this is a load displacement curve. Green line is the test backbone curve. The black line is our calibrated finite element analysis. On the right side, you see what is calibrated. So really the most significant calibration took place at the modulus of elasticity of concrete. We had to change that. But given how uncertain that parameter is inherently, we think it's reasonable. And then the yield strength of steel, we did not test that, so we took it higher than it is. It's also not unreasonable to have 70 KSI tested strength for steel. The reason why the post-cracking stiffness doesn't match is because we're using cyclic test data but monotonic loading for the finite element analysis. If we compare the last cycle, they actually match, or if we model the last cycle, they match much better. So that's our calibrated FEA. We then model the strong side to get the failure load with that calibrated FEA. So this is our failure load that we obtain and mix with our test data for retraining. Okay, now that we add this new data, I'm going to show you first the predictions for that one tested beam. So how the machine learning is doing for that single beam, and then we'll look at the overall performance. So for that one single beam, you have already seen those dark blue bars. This dark blue bar was before the algorithm saw the strong side data. So again, a very similar beam, but different reinforcing ratio. And then after we retrained it with a similar data, it actually got closer to the measured capacity. We did the same thing for our applied shear predictions. So before retraining or before the algorithm sees similar data, we had 23% error. Comparison looked like this. After we show the algorithm something similar, it did a much better job matching the test data. And then finally, this is our applied shear. So here it's a different type of situation. We had a large error to begin with before even we show the strong side data or similar data. After it saw something similar, the error was smaller, but still quite large. And that again goes back to just that limited number of data points we have for stiffness, that we did a lot of things. We filtered the data, refiltered, but at the end we concluded that we just simply need more data in the literature to do better in this. All right, and the final thing I'm going to show is again, so that what you've just seen is for that single beam. So how does the algorithm do in general for their predictions before we added new data and after we added new data? Okay, so back to my 45-degree plots again. So test versus machine learning. This tenfold error that we're using to indicate the performance of the algorithm is commonly used in machine learning. It means that we are randomly selecting samples from the data set to test our algorithm, and we're doing it 10 times, and we're averaging the error to tell you what that is. So before the algorithm sees the new data, is what we have on the left-hand side. You've seen that exact plot before. And then after the algorithm sees the strong side data, our error doesn't decrease much, 15 to 14% is not much, but our coefficient of variation actually decreases quite a bit. And we think that's because the issue that this algorithm has is really with really large size beams. So by adding even one larger size beam helps with the coefficient of variation. All right, next is our applied shear predictions. Applied shear predictions look like this before. it was already pretty good, 7% error and less than 10% coefficient of variation. It didn't change much. I don't think you could get better than this with a data-based approach. And then finally, our stiffness predictions again. We had that large scatter. We still have that large scatter, but our coefficient of variation is a little bit better. So we're happy with that outcome. Okay, so the conclusions from our entire study is first I'll make the conclusions on what we learned from testing. We learned that even though your beam may be cracked in the field, really the design codes will likely still give you conservative predictions for the capacity. For example, AASHTO, what we measured was 1.7 times what AASHTO predicted as the capacity, again, even when we cracked the beam first and then loaded it to its capacity. We observed that the transient crack widths, so the widths under the loading, are 2.5 to 5 times the residual crack widths. And that's significant again because bridge inspectors will be measuring residual crack widths versus all the test data in the literature are on transient crack widths. So we didn't really make this a recommendation because we only have one beam with this data, but it may not be such a bad idea to convert the residual to transient before you input that crack width into our user interface. So maybe multiply it by 2 based on some judgment. Overall machine learning prediction errors, as I presented earlier, are shown here. So I show the error and the coefficient of variation. This is before we tested the beam, the new beam. After we added that new beam data, we managed to decrease the coefficient of variation for shear strength and stiffness predictions. It didn't do much for the error. And it didn't really affect the applied shear predictions, which were already good to begin with. And that shows that, you may, the variety of data that you could add to the data set could make a difference because we have a somewhat different data than the majority of the data in the literature. Okay, and then the final conclusion is on that one tested beam. Like I said, we're retraining the algorithm using the strong side data and testing it using the weak side data. So for that one beam, some of our predictions did improve when the algorithm saw similar data. So for example, shear strength error decreased from 22% to 9%. We also made our applied shear predictions better, but it didn't really help the stiffness predictions much. And again, stiffness has that issue of lack of data. All right, these are our, if you're interested, our publications and products. We have one paper in review, one published, a web tool available to you if you want to go play with it, and 2 in progress.
Okay.
And let me thank everyone too. And then thank you,
Right.
TRANS-IPIC, good timing for funding us, and Institute of Bridge Engineering at University at Buffalo, and our other collaborators. Okay, thank you. So I can take questions if that's a good time.
Thank you, Pinar, so much. Very interesting work, and I'm glad that you were able finally to pull off this large-scale test. I know how challenging it is to really complete these large-scale tests. We have a few minutes for questions. The audience, what they could do is they can either type their questions in the chat box, or they can raise their hand. You can see down there the hand where you can just click on that, and then you will be given the mic to say your question, speak your question.
I can answer the ones that are already there in the text box.
Okay, go ahead, please. If you can read the question first, Pinar.
Okay. Yes, we'll do. So first question is that we, on the load displacement plot, let's see, we're there. On our load displacement plot, I said at the end of the first cycle, we already initiated shear cracking and flexure cracking. Did that happen on both sides of the beam or just one side of the beam is the question. Let me think about this. I believe this was just the one side of the beam that we observed. cracking in the first cycle, but eventually we see it in all. They were very, very small cracks, especially flexure. You absolutely cannot see it residually, but transient you can. They do a really good job closing up. Okay. Okay, so the second question is, would it be possible to strengthen the weak side so that we could take the strong side to failure? Or would it be possible to test the strong side with the support in the transfer region, so a longer span? Would that be possible? So yes, it would be. Ideally, we would have, capacity data from the strong side as well. But that would require, because we failed the beam in the weak side, that would really require another beam to be tested if we, for a larger amount of funding or longer time, we could have done that. But yeah, that would have been one way to get the information from there. And the rest of that question is the finite element model. So we're using the details of it. I didn't have much time to explain, but we're using vector 2. So it's a two-dimensional model that is based off of the modified compression field theory. So actually very interesting because it's using essentially what AASHTO is using, but not without all the assumptions AASHTO makes, and it's the capacity is much higher.
Okay, well, thank you, Pinar, so much for these answers. Any more questions from the audience? I have one quick question, then we can move on to our next speaker. Okay, Pinar, you mentioned a couple times the residual crack width. Are you, in reality, of course, in actual bridges, when inspectors go out and inspect these bridges, the self-weight is there, the deck is there. How do you think they can take this into account while still using your machine learning tool?
Yeah, so yeah, so it's going to help them see the cracks just a little bit better, but I think the cracks they see will still be much closer to the no load cracks as opposed to the transient cracks. So that's why we refrain from giving an actual number, but I would say what we observe here, this beam has almost no self-weight moment because it's such a short span compared to real beams, and we're observing, 2 to 5 times the crack width. So I would say maybe stay on the lower end of that, maybe just double the crack width and then input that into the tool.
Okay.
One option.
Thank you, Pinar, so much. Well, thanks, Pinar, again for the great presentation. I appreciate that. Let's now move to our next speaker. This project is, as I said earlier at the beginning of the webinar, I'm the PI on this project. And, as you know, TRANS-IPIC is one of the, directions of research that we focus on in TRANS-IPIC is new materials and shape memory alloys. For those who have been following us or maybe members of our team know that our center is really one of the main focus areas is shape memory alloys and their applications. So today is going to be an exciting, presentation about the project that we have been working on over the last, I would say, year and a half, couple years, with Alex, of course, is the PhD student, who continued the work, that carried on from another previous student who's now Professor Song at Ohio University. But it's a very exciting topic because it will show you hopefully how these materials could be used to develop precast components with very complex shapes and non-traditional shapes, yet you can still pre-stress them. So that's the whole point of this presentation. Particularly, Alex will be focusing today on the use of shape memory alloys in trusses. And I'll be there also joining him a little bit for if there is any questions at the end or discussions at the end of the presentation. So Alex, of course, just a few words. He joined U of I in 2022 as a PhD student. He got his bachelor's degree from UC San Diego, his master's from UC Berkeley. He worked at KPFF a little bit before joining us, so had a wide, broad experiences of structural engineering. And with that being said, Alex, please go ahead.
Okay, thank you for the introduction. I'm very happy to be here today to talk about our work on the innovative precast concrete trusses using a shape memory prestressing system. So I'll start off with an introduction into what exactly is a precast concrete truss girder, as well as some background information on shape memory alloys. I'll also talk about a numerical study as well as an experimental study, and then I'll go into a bit of preliminary results for our next phase and end with the conclusions. So to begin, I'd like to ask a simple question, which is, what are the most common bridge types? Well, they'll likely fall into two main categories. The first is a concrete bridge that's supported with pre-stressed concrete girders. And these are popular because you have the material advantage of concrete, which is good corrosion resistance and good fire resistance. The other type you might be thinking of is a steel truss bridge. These are very optimized in terms of geometry, which allows it to have a reduced cost as well as reduced weight. Now, what if we were to try to take the best of both worlds and combine this into a single bridge? Well, you'll end up with a precast concrete truss girder. So here's an example of one in France, and here's an example of one in Japan. Now, I know they look different from each other, but they follow the same design philosophy, which is to change the web of a concrete girder into a truss. This optimized geometry reduces the concrete volume, which leads to direct savings in terms of reducing the concrete material cost. It also reduces the weight of the girder, and I want to sort of elaborate a bit more on that second point, because reducing the girder weight also results in reductions in terms of costs, because first of all, when you have less weights, there's less material to transport. So the trucks that are doing delivery can use less fuel. Also, when you do reduce the weight of a girder, there's less demand on these substructures, so you can use smaller, more optimized design. In other words, even though we're just changing one element of the bridge, we are improving the bridge as a whole. Now, I want to dive in a bit more into how to design and fabricate one of these truss girders. Here I've drawn a picture of an idealized truss. If we apply an external load to this truss, the members will be either in tension or compression. Now, concrete is great in compression, but very weak in tension, so it's important that we pre-stress the tensile members of the truss to help with crack control under surface level loads. Now, the act of pre-stressing this bottom chord here, we can use just a conventional pre-stressing method because the geometry is not too difficult. It's very similar to what we use for just a conventional pre-stressed precast concrete truss girder. We can place it in a casting bed and use hydraulic jacks at the ends to tension high-strength steel strands. Now, these verticals here that are also in tension are a bit trickier to use to tension with conventional pre-stressing equipment because not only do you have multiple members to pre-stress simultaneously, you also need to think about having clearance at the top and bottom of the beam for the equipment. You also need to consider these strands in the verticals will intersect with the strands in the bottom chord at the joints. And so we're proposing to use a new form of pre-stressing called shape memory alloy thermal pre-stressing. And this will resolve the issue by eliminating the need for hydraulic jacking equipment. It eliminates the need for external anchorage. It also solved the problem of the intersection of the vertical pre-stressing steel with the bottom chord's pre-stressing steel. And ultimately, it will provide more localized pre-stressing. Now, before I can explain how shape memory alloy pre-stressing works, I'll provide a quick background on what exactly is a shape memory alloy. So shape memory alloys, they're a class of alloys that possess different crystalline phases, And by switching between these phases, it creates a shape memory effect. To help illustrate this, let's imagine we have this a bar of SMA here. We can stretch this out beyond its elastic limit to permanently deform it, so it goes from martensite to a deformed martensite phase. Now at this point, if we apply heat to this bar, the SMA will change phases to austenite and remember its original length. Now if we want to use this principle for pre-stressing concrete, we start with the same steps. We take a bar of SMA, pre-strain it. Now at this stage, we add the additional step of placing it inside of concrete, which constrains it from movement. And applying heat at this stage causes the phase transformation, and the SMA imparts a recovery stress onto the concrete. And this recovery stress is what pre-stresses the concrete. So the first step our research group took in exploring this concept was a numerical study, and this was done by a former student, Professor Andrawes, whose name was Min-Soo Sun. He analyzed a bridge supported by 5 of these concrete truss girders. The girder geometry was designed by taking an AASHTO Type 2 cross-section and converting the web into a truss. Now, the pre-stressing methodology is similar to what I described earlier, where the bottom chord uses conventional high-strength steel strands, and the verticals use the shape memory alloys for pre-stressing. The performance of this girder was compared against a standard AASHTO Type 2, and what we found was that the concrete truss can reduce the volume concrete by 38% while still meeting the limits to satisfy a strength 1 limit state. So these are very promising results, and our next step was to validate it experimentally. To do so, our research group studied the recovery stress of a 1/4-inch diameter nickel titanium niobium bar. This was done by constraining the bar and heating it up to 428 degrees Fahrenheit. And that caused it to produce a recovery stress of 40 KSI. The bar was loaded again after activation, and this is the corresponding stress-strain curve. Now we want to use this information to design 2 different tensile members of a truss. We want to design one tensile member using steel and one using SMAs. We know that for grade 60 steel, regardless of whether you machine the cross-section of the coupon, it yields at around 60 KSI. Now, if we look for a similar point on the SMA curve, we see 40 KSI. So we decided to compare the strength of 6 1/4-inch diameter steel bars against 8 1/4-inch diameter SMA bars. To design the truss, we followed the same approach as mentioned before, where we take an AASHTO Type 2 and modify its web into a truss. We used the 6 1/4-inch diameter steel bars in one of these tensile members, and for the other one, we used 8 1/4-inch diameter SMA bars. Now you'll notice that these 8 bars aren't distributed uniformly. Instead, we have them grouped into pairs into the corners of this member, and that was done so that when we heat these SMA bars to activate them and trigger the shape memory effect, we can heat pairs of SMA bars at the same time as opposed to one by one, which speeds up the process. I'll talk a bit more about the heating procedure in a later slide. Here's an image of what these SMA bars look like before they're placed inside concrete. You'll notice they have a smooth surface, so what we did was we added these copper crimp connectors along the length of the SMA bars, and that's going to help it engage and bond with the concrete. We also have a thermocouple attached, and we'll be using that to monitor the temperature of the SMA when we heat it up. Now I want to talk a bit about the fabrication process. The first step was to assemble the reinforcement inside of the formwork, and this was done by tying all the bars together with rebar ties and supporting them on top of rebar chairs. We used 8 of these triangular foam blockouts to form the shape of the voids in the truss. Then we closed everything up and added a series of braces along the outside to support it against the concrete lateral pressure. If you were to look at this point from top view, after we've closed everything up, you can get a sense of how slender these members are and how much rebar congestion we are dealing with. So we had to be very careful of how we approached pouring the concrete. Specifically, we began pouring concrete from the center of the specimen, and our goal was to have the concrete flow from the center outwards to the ends and completely fill the bottom core before we tried pouring concrete at any other location. And by doing so, we can ensure that we aren't trapping any air pockets underneath those foam blockouts. So we kept filling, and then right around the halfway mark, the formwork actually flexed at one portion. So you can see in this image, we had to go in with a couple extra clamps to provide additional support against that movement from the concrete pressure. And because of the rebar congestion, we weren't able to put the vibrator into the concrete to remove air bubbles. Instead, what we had to do was use the vibrators externally and vibrate the formwork. Now, once the concrete hardened, we could begin demolding the specimen. This proved to have its own challenges because the foam was actually very, very tightly squeezed by the concrete. And so you can see in this image, in order to get the foam out, we had to chip it bit by bit away from the concrete. On this side, you'll see that there are some voids in a diagonal member of the truss. And this was the location in the previous slide where I mentioned how a portion of the formwork began to flex under the pressure of the concrete. So that movement of the formwork sucked in a couple of air bubbles at that location. Fortunately, it was very easy for us to just patch this up once we fully demold the specimen. You also notice that there are some bars protruding out of the specimen. We use this to later add on footings, and this is to help with the stability of the specimen. You'll see in this image of the finished specimen that we painted everything white to aid in the visual identification of cracks for later during the testing process. Now, you might be wondering how exactly are we going to heat the SMA bars now that we've encased them fully inside of concrete? And the answer is to use electromagnetic induction. So this works on the principle of having a coil through which you run an alternating electrical current. This current, as it goes through the coil, generates a changing magnetic field, and this magnetic field passes directly through concrete without heating up the concrete, and only nearby metals will react to this magnetic field. So nearby metals like SMAs will be heated up without direct contact. Our research group has used this technique previously with great results, so we are excited to use it on the truss. Over here is an image of what that setup looks like. You can see we have the induction coil placed up against the specimen that contains the SMA bars. Once we turned on the coil, it began to heat up the SMA bars inside the concrete without direct contact. You also notice that we have a series of dots on the surface of the concrete, and this was so we can use a digital image correlation software to track the longitudinal strains. And I'm going to play an image. This is a time lapse of the process. So this is the SMAs being heated up as well as cooling back down to ambient temperature. And you can see that this blue region in the middle is indication that the concrete there is being compressed by the activated SMA bars. We also had strain gauges attached to the specimen, and by using these values, we can equate the amount of force being developed in the concrete to a pre-stressing force of 8 kips. So once we pre-stressed everything, we moved it into a 3-point flexural test setup. We have an actuator at the top, a load cell between the actuator and the test specimen to measure the applied load, a laptop and a data acquisition system to record all the data. We have 2 lights, one for monitoring each specimen, as well as 2 cameras, one to monitor each vertical member of the test specimen. And we also have an LVDT to measure the vertical displacements of the test specimen. So in this current orientation, the steel member is on the left-hand side, and the member that has the SMA bars is on the right-hand side. So we began loading, and you'll notice that there is a slight change in stiffness. That was just due to rotation and a little bit of settlement at the supports. When we reached about 5 kips of applied load, by using digital image correlation, we detected cracks in the upper joint on this member that has steel reinforcement. And this is indicated by DSE, or digital image correlation, in red. At the same time, on the same sort of mirror image, with the SMA side, we don't detect any cracks. We then kept loading it, and when we reached an implied load of 10 kips, we saw signs of cracking, this time at the lower joints on the steel side. And similarly, like before, there was no signs of cracks on the lower joints of the SMA side. We then continued loading, and when we reached around 12.5 kips, you'll see there's a sharp decline in stiffness, and that was because the bottom cord had cracked at this location. And we continue loading after this point. You'll notice that the stiffness is a bit different now that the bottom cord has cracked. And when we reached an applied load of 15 kips, we detected signs of cracking, this time 2 horizontal cracks at the middle region of that concrete tensile member reinforced with steel. Meanwhile, there is no cracks being detected at that middle region on the side that's been pre-stressed with SMAs. So we were able to conclude that the SMA pre-stressing was effective at increasing the crack resistance of the concrete tensile member. Now, for our next phase, we're going to conduct another numerical study. Similar to before, we will take an actual type 2 cross-section and convert the web into a truss. And we'll use SMA pre-stressing in the vertical members of this truss. But what we'll be doing differently is to explore the effect of removing different volumes of concrete. Another thing we're doing as part of our next phase is to use 3D concrete printers to produce these trusses. You might remember from the previous slides that there's a couple of challenges that come with using conventional formwork. For example, you have to fabricate the truss. Fabricate the formworks, which uses material and time. You also have to consider how these members are slender, so there's a lot of reinforcement congestion going on. You have to then demold the specimen, which is also difficult, and you can't use vibrators inside the concrete, so any sort of trapped air is just there until you demold. If we were to use a 3D concrete printer instead, we can eliminate all of these challenges. There's no need for formwork, so you solve the problem of having to fabricate formwork as well as having to demold the formwork. You'll see later that the way we integrate reinforcement eliminates the issue of rebar congestion. And also, since it's a printed concrete that's extruded from a nozzle, there's no need to vibrate this concrete. We partnered with Alex Construction. They're a leader in this field of 3D concrete printing. Here's a video of what that printing process looks like. So a computer-controlled nozzle extrudes concrete in the shape of the truss. Now, to add reinforcement, we simply just lay the bars in between these printed layers. So that eliminates the need for tying the rebars together or having rebar chairs. And this is how we solve the issue of rebar congestion as well. Once it cures, there's no demolding process, and it's ready to be delivered as is. So we're very excited to test this and share the results of it in the near future. In conclusion, the truss geometry uses material more efficiently, and by coupling this with SMA pre-stressing, we can reduce the concrete volume by up to 38%. Also, the SMA shape memory effect produced 8 kips of pre-stress in the concrete truss test specimen without needing hydraulic jacking equipment or external anchorage. The DSE and strain gauge results show that the truss tensile specimen with SMA pre-stressing had greater crack resistance than the truss tensile member that was using just conventional steel reinforcement. And lastly, by using 3D concrete printers, we can greatly speed up the fabrication process of these concrete trusses. I'd like to thank you all for your kind attention, and I'd like to thank my advisor, Professor Bassem Andrawes, as well as TRANS-IPIC for their continued support on this project.
Thank you, Alex, so much. We have time for maybe a few questions for Alex, and I will participate in answering the questions as needed, of course. I think there's one question in the chat, maybe a couple questions. Alex, can you read them, please, and see if you want to answer them?
Yeah. So the one in the chats, that one's not for me.
It's in the Q&A. Yeah.
Oh, I see it. Are the SMA bar? The question was, are these SMA bars available commercially? And I guess the short answer is yes. But definitely, I guess the longer answer is that there's not quite as much demand for it by the civil engineering industry. It's primarily being used by aerospace and the medical field. So they're available commercially, but hopefully with this research, we can start to encourage it to become more popular amongst the civil engineering industry.
And if I maybe can add also, Alex, that the bars that we talked about today and Alex presented his work on, those are, as maybe I mentioned earlier in our workshop a couple times, they have been treated in much less intense from a thermomechanical treatment perspective. So the cost is much, much less than what we typically see in high-end fields like medical field or maybe aerospace field. So I think the industry realizes now, talking about the SMA industry, realizes the potential of producing these bars in such, with such specific characteristics for civil engineering applications. And maybe it's not suitable for other applications, but for civil engineering, and that brings the cost down quite a bit now. But yes, they are available commercially. I think, Alex, there is another question.
Yeah, another question coming in. The question is, how are you designing the nodes of the truss? I think a lot of people have anxiety about concrete trusses due to the bridge collapse in Florida. I saw some patches with 3D printed at the nodes. So I guess this is a two-part question. Definitely the nodes of the truss are critical. I agree with that. Um, the way we designed it for the precast version, I guess if I go backwards, sort of to this one, we approached this simply as just, let me go back a bit more, maybe this is the best picture. We approached it so that we wanted the nodes to be within the web. If I can turn on a pointer. So what I mean by that is that some of the considerations we had was that we want the node to be fully between the top and bottom chord, so that way we're not really interrupting the continuity of that top and bottom chord. And I guess the other consideration we had was to try to address stress concentrations by rounding out the edges of these joints. But definitely this is an area, like these joints in particular are something that we can definitely look more into and study in greater detail. I guess the second part of the question was about the 3D printed concrete version, so I will go to that one. Yes. Oh, okay. So the question was about the patches here at the 3D concrete printed version. I want to just clarify that the patches there were not really because there's like an error in the printing. What we had to do with modifying, with I guess adapting the geometry of truss to this printer, which was really designed for printing buildings, was to have essentially, how do I put this? We had to draw the path of the printer in a way that it did not intersect. How do I phrase this? We rearranged the printer lines in a way to make it print in the most optimal manner possible. But a consequence of doing it that way is that at all the joints, these lines of printed lines are not going to perfectly mesh together. So you can see in this left-hand side, there are some gaps where we had to patch it with concrete. And this patching was done almost immediately, sort of after this concrete was printed, we added in more concrete to fill in those gaps. So it's sort of not an error not like before, where we had air bubbles that we had to then patch with grout. This is sort of an intentional void left in the design that we immediately infilled as it was still fresh concrete. So I would argue that this type of patching was really as strong as if it were printed. So I would say definitely joints in conclusion. Definitely joints are something that we can study a bit more of. But I just wanted to sort of distinguish that there's the patching done on the precast version is different from the patching done in the printed version. The patching done with the printed version was intentional, and it was added in while the concrete was still fresh.
Okay, well, thank you, Alex, for these responses. Is there any more questions for Alex on this presentation? Well, if nothing, then thank you again. I'd like to thank again, the presenters. I'd like to thank the audience, those who attended today. And as I said, next month there will be a faculty meeting, so there will be no webinar. But we look forward to seeing you again in August webinar. Thank you all, and have a great rest of the day. Bye-bye.
Bye. Thanks, everyone.